Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.
Hello everybody, and welcome to this second edition of our Enclustra live webinar, which is part of our Enclustra webinar series. My name is Monica Sanchez Mesa. I am the Senior Marketing Specialist at Enclustra, and it's a pleasure to have you here today. This webinar, again, is the result of the feedback that we received from our seminars in the East and the West Coast of the US, and also from our last webinar on Python code simulation. You asked us for high-tech topics on our latest developments directly to high-skilled engineers. So this time, we bring you this topic, software-defined radio with Zynq UltraScale RFSoC. And today, we have people registered from all over the world. We have people from Armenia, Austria, Belgium, Brazil, Canada, Croatia, Germany, Spain, France, UK, Israel, India, Mexico, Malaysia, Netherlands, Norway, Pakistan, Poland, Romania, Serbia, Singapore, Turkey, and the US. And now, please let me introduce to you to our team in sales. They are backstage to help you with any kind of question, and also if you have any type of projects already, they will be very keen to help you and assist you to and put you in directly with our design services team. From headquarters, our recently appointed VP Sales and Marketing, Heinz Glor. We also have our Senior Global Director of Sales, Roland Paul, and Marco Hennespegger, who is the Head of Account Managers. But also, we have our representatives from the US and Canada. We have Avery, we have Tristan, and also we have Patty. From Germany and Austria, we have Harmut, and we also have Johannes. And finally, from the rest of the world, we also have Shlomi, Vincent, and Amber. If you have any questions during the presentation, please use your chat that you have for on LinkedIn and as well on the StreamYard. If you want to put your questions, we will gather these questions and we will collate them. And after the presentation, we will do a question and answer session. But also, if you have any projects or you have any other things that you want to share with us, please send us to us, webinars@enclustra.com. And if you want to receive the presentation as well, or maybe the recording of the presentation, please write to us. Also, if you haven't already, please follow us on LinkedIn, YouTube, and X. Also, if you have a project, please contact us at sales@enclustra.com. We will be very happy to assist you in any project that you may have. And now let me introduce to you to our expert for today. Our expert for today is our senior RF hardware engineer, Dr. Johannes Hermann. Dr. Johannes Hermann was a distinguished postdoctoral researcher at ETH Zurich Quantum Device Lab, focusing on quantum machine learning with superconducting qubits. He has a wealth of experience, having designed quantum-limited microwave amplifiers. Previously, he excelled as a radio frequency hardware design engineer at Zurich Instruments, developing hardware superconducting quantum processors. Dr. Herman also gained valuable experience in autonomous driving technology during his time on Porsche. Johannes, welcome to the studio. The stage is all yours.
I think, can you see my slide set?
Yes, now.
Yes, now we can, yeah. So thank you for the introduction, and also I would like to welcome you to this webinar about a software-defined radio with the Zynq UltraScale Plus RFSoC. So let me first give you an overview of the content which I will present today. So first, I would like to talk about the Zynq UltraScale Plus RFSoC and also the hardware which goes with it, which we will make use of in today's webinar to implement actually live a software-defined radio on the RFSoC. Second, I want to focus on the generation and acquisition of RF signals in the gigahertz range. And I would first like to explain you a little bit the theory about how to generate RF signals with the RFSoC. I will show you some measurements, and I would also like to focus on how to exploit sampling in higher Nyquist zones to generate high frequency signals, and with that unleash the full capabilities of the RFSoC module. And then in the second part of the presentation, I will focus on the software-defined radio implementation, where I will explain to you how a software-defined radio can be implemented on the RFSoC. And I will, in the end, give you a live demonstration of the hardware running a software-defined radio. And in the end, there will be time for a conclusion and also questions from your side. So let me get started with giving you an overview of the AMD Zynq UltraScale Plus RFSoC. So the RFSoC itself is very similar to a standard FPGA where you have a processing system, and a large part of it is also a programmable logic. But the special thing about the RFSoC is that it has dedicated data converters for processing high-speed signals. So it has numerous ADCs and DAC converters, which can directly synthesize microwave signals. And in the case of the RFSoC, which we will make use and have a look at in this presentation, there are 8 RF ADCs and 8 RF DACs included, and those can generate and acquire signals up to 7.1 gigahertz in bandwidth. And what this number means, I will also like to explain you in this presentation a little bit later. So let's first also have a look at the hardware, which we will make use of in this webinar. So here I have a picture of the system or the module which we have built, and we will make use of this module to implement a software-defined radio in this webinar. So this module features the RFSoC generation 3. So the model is the XZU48DR. It has a capable programmable logic and also a processing system, but most importantly, it has these 8 data converters for our 8 RF ADCs, which can sample up to 5 gigasample, and also 8 RF DACs, which can almost sample up to 10 gigasamples. And the module also features memory, which can interface the RFSoC, and in our case, we have 8 gigabit DDR for the PS and 8 gigabit DDR for the PL. And also on the module itself, we have power converters which allow the module to be operated from a single power supply voltage. And if we now look at the bottom side here of the module, we can see that there are 5 high-density connectors, where the top 3 of them are meant to carry power to the module and also interface the digital periphery of the RFSoC. And we will later see that these will connect to a baseboard in our setup. But we also have those 2 special connectors which have a different pin out, and they're here at the bottom. And those are just meant to purely carry the high frequency signals towards the ADCs of the RFSoC and from the DACs of the RFSoC. And this will connect to an RF front end, which I will show you actually on the next slide. So the full hardware setup looks as follows. So that's a picture from the top. So here in the middle, we actually have the RFSoC system on a module with a generation 3 RFSoC mounted. Then here on the bottom, we have the digital baseboard, which provides power to the module and also allows to interface the digital periphery of the RFSoC. And then connected to those special connectors for the RF signals, we have the RF front end, which here in this case is just a fully passive front end that directly connects the output of the DAC to some high frequency connectors, which you can see here at the top side of the module, and also the ADCs are directly connected to the RFSoC, and also we have a low phase noise clock source on this RF front end. So having had a look now at the hardware which we have available, I want to now jump into theory and actually have a look together with you on how you actually generate RF signals using the converters inside the RFSoC and what is special about it and what you have to look at. So fundamentally, what a data converter wants to do is it wants to translate the digital representation of a signal into the analog domain and vice versa. So we want to go from signals that digitally are discrete in time and amplitude to the analog domain where the signals are continuous in time and amplitude. And in this webinar, because time is limited, I will just focus on the generation of RF signals. So we will have a look at the RF DAC and how it can be used to generate the RF signals. So let's go to the theory side first. So here on this slide set, I will now show you how the signals are generated and how it looks like from a signal processing perspective. So on the left-hand side, you always have the representation of the digital domain, and on the right-hand side, you have the analog domain. And in the middle sits the data converter, the DAC. And now in this example, our task is just to generate a sine wave of frequency f1, which I have sketched here with this dashed line. And ideally, the frequency spectrum of the signal, if this is infinite long, is just a single delta function centered at frequency f1 here, the positive frequency range. So what happens if we actually now go to the discrete representation of this? So when we sample the signal, we now are discrete in amplitude and time. So this I've expressed here by sketching the values of the sine function with these purple dots. So we have these dots, and mathematically we can express this by multiplying our signal with the train of delta functions that have the distance of the sample time. And what that leads to in the frequency domain is that due to the sampling, we not only get the frequency component which we want, which is at frequency f1, but we also get the frequency copies, like aliases of that frequency, which is centered around the sample frequency. So depending on the sample frequency which we choose in order to sample the sine wave, we will get alias copies of that signal centered around the sample frequency. So you see that you have a lot of high frequency components in the spectrum. And so now the question is, this is all in the digital domain. What happens now if we go and feed the signal, this digital signal, so the stream of data, into the DAC converter? What will it do? So in principle, the DAC will not, in the end, be able to put out delta functions of just this height, and we also don't want that. So what it will do in the real world is it will produce an output which looks like, which I show you here in the time domain, and it will sample and hold the output until the next sample is shifted out of the DAC converter. And so mathematically, we can write this, this processing what the DAC is doing in the real world as a convolution with a rectangular function where the width is the sampling duration. But what that leads to in the frequency domain is, interestingly, if you do the math, so you can just calculate the Fourier transform of this expression, and there you will see that the rectangular function will be then transformed into a Zynq function, and the convolution will equal to a multiplication. And I've tried to sketch this behavior here at the bottom right side. So you will see that the original spectrum of having a lot of higher frequency components that are equal in magnitude now goes to the situation where the high frequency components are attenuated by this so-called Zynq roll-off. And this just comes from the fact that the DAC implements a sample and hold output. But in the real life, what will also happen is that you will get additional attenuation for larger frequency components from the limited bandwidth of the DAC converter. Meaning the higher frequency signals, they experience more loss when they travel out of the DAC converter, and also when they go outside the DAC converter on the PCB and to the arrive at the connector. So there will be a frequency dependent loss, which actually adds up to that trend that the higher frequency components have less magnitude. But what we have to say that this bandwidth in case of the RFSoC is relatively large, meaning that we will still see this frequency copies, but we can also make use of them. That's what I will show you on the next slides. So now I want to go and show you some measurements, which actually show where you will see that we have this kind of behavior. So, so what I did is I went to the lab, I took the setup, which I've shown you in the beginning, and I have programmed the RFSoC to generate a sine wave of frequency 500 megahertz with a DAC converter running at a sample frequency of 2.5 gigasample. And then I simply connected to a spectrum analyzer, and we now will have a look at what the output looks like. And in the time domain, let's remind ourselves, the behavior will be a sample and hold. And in the frequency domain, we now expect to have this spectral copies due to the sampling visible in the spectrum. And we should also see that the trend with larger frequencies, we will have less power. So this is the result of the spectrum. And so maybe let's try to identify all the peaks, which we can see here. So first of all, we see some leakage of the sample clock to the output of the DAC converter. So sample clock is 2.5 gigasample. So we see a signal at 2.5 gigahertz and at 2 times the sample frequency also. But we also see clearly the signal we intended to generate. So that's the sine wave at 500 megahertz with 0 dBm power. But we also see, as we have discussed and as expected from theory, the aliases of that signal centered around the sampling frequency. And we also see clearly this trend, which is the sum of the effect that we have the roll-off due to the Zynq, but also due to loss, which is frequency dependent. And now we can assign names to those zones. So clearly the first, so up to the half the sampling frequency, you call this frequency range the first Nyquist zone, up to the sampling frequency there in between the second, third, and fourth. And those names will be important later when we want to try to talk about how to exploit higher Nyquist zones. That's the frequency range, which I indicate here, to make use of this to generate high frequency signals. But let's first focus again on this measurement. So in the end, like in the beginning, our task was to generate a 500 megahertz sine wave. And now we have all the spectral copies. So these are high frequency components. And we don't, so if our task was to just generate that sine wave of 500 megahertz frequency, we have just failed because now we have this high frequency components. So in order to solve that, what we do is we use a low pass filter. And this low pass filter in now this scenario, which I present you here in the measurements, has a cutoff frequency of about 1 gigahertz. So meaning all the frequencies which are above 1 gigahertz, they will be attenuated by the low pass filter or reflected. And so what I do, I now take this low pass filter. We have this measurement here. So that's without the low pass filter. And that's the time domain representation of the signal. And now once I install the low pass filter in the output path of the DAC, what will happen is the high frequency components will disappear, and I in the time domain have just a smooth sine signal, and I have generated actually the sine wave which I originally wanted to do. And now let's jump to a different scenario, and now let's formulate a task that we want to generate a signal. So in that case, a 3 gigahertz signal in the second Nyquist zone. And how do we do that? So in that simple case, I will now program the RFSoC to generate a sine wave of 2 gigahertz frequency. And now we sample the DAC converter with 5 gigasample. And let's just have a look at what the output of that is and then see how we actually use the second Nyquist zone to go to 3 gigahertz signal. So the output of that setting looks as follows. So here, let's remind ourselves again, we produce a sine wave of 2 gigahertz frequency, we sample with 5 giga sample. So let's try to assign again the peaks in the spectrum to what we know it is. So here at 5 gigahertz, we see the sample clock leaking through the output of the DAC converter. But then we see these 2 peaks, and one of them is the 2 gigahertz signal in the first Nyquist zone, and the other peak is actually an alias of that in the second Nyquist zone. And now, if we just say we want to generate a 3 gigahertz sine wave, what we simply do is we use a bandpass filter in that case to just pick out the frequency component which we would like to generate. And in the time domain, the signal now looks as follows. So you see there are sharp edges in the signal. This means there are a lot of high frequency components. And now we put a bandpass filter, of which I have indicated the cutoff frequencies here with the gray zone. And what it will lead to, it will attenuate the other signal in the first Nyquist zone and just pick out the signal which we want. And like this, we now have generated an RF signal which is larger than half the sampling frequency. So we went beyond the Nyquist limit and synthesized now a signal using a bandpass filter in the second Nyquist zone. So let's briefly summarize what we have learned in this section of the webinar. So we have seen that a high sample rate data converter can be used to directly generate analog signals at radio frequencies. And here we're really talking about gigahertz frequency range. And what we have seen is that we always need a reconstruction filter to generate the intended signal. And also using a filter which filters for signal copies in higher Nyquist zone allows you to go beyond the Nyquist frequency limit of half the sampling frequency. And ultimately, the maximum signal frequency which you can achieve with your data converters is limited by the bandwidth of your output, so the DAC plus the circuitry which comes afterwards. And so let's briefly compare this approach of directly generating RF signals, as you've seen with the RFSoC, to the traditional approach where we actually use a frequency conversion stage. So here on the left-hand side, we have the traditional approach, where typically what is done is you take a DAC converter, which samples at the intermediate, which samples with the intermediate frequency, and then subsequently you have a frequency which is like in the 100 megahertz range typically, and you use an analog mixer to upconvert the signal to the gigahertz frequency range, and then you filter for the desired frequency component. In contrast to that, the direct RF generation approach just relies on having a DAC converter, which is fed with a very high sample rate, and then you just need one filter in order to get into the gigahertz range. And if you compare these two approaches, we see that actually this traditional approach of using frequency conversion and an analog mixer is complex in hardware, since you need an analog mixer, you need a local oscillator, which is a continuous microwave signal in that case, and you need also filter. And also in this approach, the signal bandwidth is limited because your data converter is running at a low sample frequency, and typically that's like about several hundred megahertz. In contrast to that, the direct RF generation approach is simple, since you just need the DAC and the filter, and you can achieve a relatively high signal bandwidth, which is just limited by the sample frequency. And in the RFSoC, everything is integrated. So the DAC is there, and you can directly synthesize the RF signals. And what you can also do is you can achieve excellent phase noise of the generated signals if you provide a high quality sample clock directly to the RFSoC. And so, having now learned about how to generate RF signals using the RFSoC, I now want to jump to the second chapter of this presentation, where we'll focus on software-defined radios and how they can be implementing using this technique and also on the RFSoC itself. So what is a software-defined radio? So let's start from there. So a software-defined radio is a communication system where the conventional analog components, which are found in radio hardware, are actually implemented in software. So what you typically have is you have these ADC and DAC converters in the software-defined radio that allow you to process the microwave signals, which are coming from the antenna and sent to the antenna. Then you have a digital front end, which is doing some pre-processing on the digital signals, and then some baseband processing, which in the end allows you to interface an input data stream and also have an output data stream. And the only thing you need to attach to it in that case here to make the picture complete is that you have, if you want to transmit also the data wirelessly, you need a RF front end connected to the DAC, which in that case just consists of a proper filter and a capable amplifier. Then you have an antenna, and in the receiver end you have the opposite. So first you would actually have a low noise amplifier and some filtering before you go into the ADC. And now I want to have a look at how such an architecture could look like on the RFSoC. So on the RFSoC, we can actually build everything on a single chip. So we have the data converters being interfaced with the front end where the radio signals are coming from. So then inside the programmable logic, we can implement the digital front end and also the baseband processing. And also what can be handled by the RFSoC is that its processing system can be used to interface the programmable logic and the baseband processing. And in the example, which I will show you today, we will actually implement Linux. On top of it, we will have Pink, which is a Python utility for the RFSoC, and allows you to actually with Python configure the RFSoC hardware. And on one layer, even on top, we will have a Python, so a Jupyter notebook running, which allows you to play with the settings and also to inspect the data which is transmitted and received. And in a particular, what I will now focus on is the example which I will present today, and that's the implementation of an orthogonal frequency division multiplexing scheme. So I will explain you in a minute what it means and what the advantages of it are. And we have adapted this OFDM modulation scheme and implemented on the RFSoC. So let me now focus on this OFDM modulation scheme and explain you a little bit about the advantages of it before we go to the live demonstration. So as I said, OFDM stands for orthogonal frequency division multiplexing, and why that the name is like this, I will explain you in a minute. And it's a widely used multi-carrier modulation scheme used in 4G LTE, for example, 5G new radio, and also Wi-Fi. And one of its big advantages I will want to explain you on this slide. So let's start from the beginning. So if you want to transmit data wirelessly, what you typically do is you have a carrier frequency and you modulate the information on top of this carrier. And so here I've sketched the situation of how this looks like. So here's we see a spectrum. Here is the carrier frequency. And if you want to have a lot of information in your signal, you also want to occupy a large bandwidth given a certain signal to noise ratio. And so what you do is you have this spectrum and you send it to your transmitting antenna. And in the ideal world, this signal would just travel to the other side where you have the receiving antenna. But in the real world, that's not the case. So what the signal will do is actually it will take multiple paths. And this multiple path could look like the signal is going in that direction. There's an obstacle, it is reflected, and then it's going to a receiving antenna. Then there's the direct path, and there might be multiple other paths where reflections occur. And the problem with that is that all of these signals, they will interfere in your receiving antenna. And since there are different time delays between all these paths and also different amplitudes involved, what this results to that the interference will create you a frequency dependent transmission of this so-called channel. So meaning frequency signals of different frequencies will experience different amplitude and phase shifts. And in your receiver, what this will lead to is that the original intention of you transmitting this uniform block and the frequency spectrum will result in something like this. And that's what the receiver end you don't want. So you want to have, again, equal power for all the frequencies you're sending. And what you then need to do is actually to invert this channel transfer function and apply it to the received signal. But the problem is that since this is very broadband, this is very difficult to do and computational very expensive. And now OFDM comes into play because it allows you to do this complex computation very efficiently. And why so? So instead of transmitting this huge block in the frequency domain with a large bandwidth, what you do is instead you have multiple carriers with a narrow bandwidth. So you have a lot of carrier frequencies. You modulate your information on each of these subcarriers, how to call them, and these are now transmitted through the channel. And now each of these subcarriers will experience an attenuation, an amplitude, and a phase shift depending on the channel transfer function. But the important thing now is that we are operating this in a limit where we can assume that the variations within the subcarrier of this channel transfer function is approximately flat. And this leads to the fact that you can actually efficiently correct for this frequency-dependent transfer. Because what you then in the end need to do is just multiply each of the subcarriers with one amplitude and one phase. So it's easy to compensate for it. So that's the first advantage of OFDM. And now let me focus on the second aspect of OFDM. It's about that it makes use very efficiently of the frequency space that is available. So as I said, in OFDM, what you do is you modulate your information on different subcarriers. And this I've tried to express here with this sketch. So you have a stream of input data, and this input data, you then use a serial to parallel conversion of factor 1 to n. So you then have slower streams of data here, which are then all modulated on top of the subcarriers. And in the frequency domain, this will look like in the picture you have seen before. So you have these multiple subcarriers, and you have them with a narrow bandwidth. And since you don't want the subcarriers to interfere with each other, what you then naively would do is you would just space them in frequency with a certain distance such that they don't interfere. But the problem is the frequency space is limited, so you want to actually minimize the space between the subcarriers. That's actually what OFDM allows you to do. So OFDM allows you to kind of overlap the subcarriers. And why is that so? So if you look at the OFDM subcarrier frequency spectrum, it is again a Zynq function because you send off blocks of data, and blocks of data, rectangular, corresponds to Zynq in the frequency domain. And if you choose the subcarrier spacing correctly, so in relation to the bandwidth of each subcarrier, then you can create a situation where actually the zeros of the Zynq function all agree with the frequencies of all other subcarriers. And that's why you call OFDM orthogonal, because these are then orthogonal function at the frequencies f1, f2, and f3. And you can now make very efficient use of the frequency space that is available. And there's a second advantage also, a third advantage of the OFDM modulation scheme, and that's about that you can implement this modulation, which I've shown here on the sketch, very efficiently. And why so? So then let's have a closer look to what this modulation actually corresponds to. So here I said that each subcarrier has a frequency f1, f2, and fn. And now let's express this by modulating the stream of parallel input data by this complex exponential, which in the end is just a sine and a cosine function, which oscillate with frequency f1, f2, and fn. And if you now do the math and you add all of the signals up, you will get a sum which looks like this. And now the nice thing about this property is that these frequencies f1, f2, and f3, they are all equidistant, meaning they all have the same frequency difference between them. And so you can write them in a sum. And the sum looks as follows. And the nice thing about it is that this sum actually is the expression for an inverse Fourier transform or inverse fast Fourier transform in a digital domain of the input signal. And as we know, the fast Fourier transform algorithm can be implemented very efficiently on the digital hardware, and that's also one why OFDM is so widespread, because this can be done efficiently. So let's go back and look at our software-defined radio once we now have understood some details of OFDM. And let's focus on the example where we actually want to implement this. So as I said, we will use the RFSoC to implement the software-defined radio. And inside the programmable logic, we will implement the OFDM transceiver, where the DAC its task is to generate the transmission signal, where the symbols are generated here in that unit in the programmable logic. And I will show you also on the next slide how that is done. And then the OFDM transmitter provides the data to the digital up conversion and some interpolation before it reaches the DAC converter. And at the receiving end, we have exactly the opposite. So you have the ADC, a digital down conversion with decimation, and then the OFDM receiver. And then on the right-hand side in the processing system, we will have the possibility to play around with the settings of this OFDM transceiver and look also at the data which we receive. But now we first, in order to understand what we actually are seeing later in the live demonstration, we need to have a look at how the symbols are generated for the case of this OFDM example. And so each of the subcarriers, which we have seen before, can be modulated. So each of these individual subcarrier can be modulated using different well-known modulation schemes. And this then relates to how the data, so in our case, this is a random stream of bits which go into the subcarrier modulation, how they actually translate into the OFDM, into the analog signal. And so here, what in our demo we can do is we can play around and try out different subcarrier modulation schemes, where the most simple modulation scheme I want to explain you here is a binary phase shift keying modulation. So here the information of the input is encoded just in two different possibilities of how the phase of a cosine signal could look like. So in that example here, I have translated that the information 1 corresponds to a cosine which starts with a phase of 0, and if you would transmit zeros, that would correspond to a phase of 180 degrees. And this we can also see here in the IQ plane. So we have one bit which we can transmit with this modulation scheme, where we use two different phases of a cosine wave to encode our information. But then in our receiver, we will see later that we can change the modulation scheme and go to something more complex. For example, we can go one step further and say that we want to implement, for example, a quadrature phase shift keying. So here we allow 4 different positions of the phase, and we can encode with this 2 bits. So the phase can now take 4 different values, and then you can assign 2 bits to this, and this allows you to even enhance the data throughput because you can modulate more information on top of your carrier. And then our example will also allow you to go even further and, for example, implement a quadrature amplitude modulation, which makes also use of different amplitude values in order to even encode more information into your signal. And now, having looked at that, I want to go to the demo hardware and show you the live demonstration. So what we have done is we have taken the board, which I've shown you in the beginning, and we have adapted this software package, which is publicly or is open source available from this GitHub repository, and we have adapted it to work on our hardware. And what we also have to do now in our demonstration is that since we are not allowed to transmit at any frequencies signals into free space, since there are some legal regulations, what we have to do is we have to use a cable to connect the transmitter with the receiver. So there's a hardware loopback cable installed in the setup here at the RF front end that connects the output with the input in order to make our hardware demonstration. And also we have an Ethernet cable connected to the setup that allows you to communicate and get the data back with a computer. And also the sample clock for the DAC and ADC converters is generated by this low phase noise oscillator, which is on our RFSoC front end. So now, having said this, I want to go and swap my screen to show you the live demonstration. But before that, I also want to mention again that if you have any questions, you can forward, or like you can write to this email address, which I have here on the bottom right. And now I will change my screen and we will play around with the OFDM transceiver. So I hope you can still see my screen and everything works. So now I have opened actually Jupyter Lab, which is running directly on the RFSoC. So inside its processing system, we have Linux, we have this Zynq, this Python utility, which allows you to configure the RFSoC hardware. And on top of that, we have this Jupyter notebook, and that's actually now what we are controlling. So this stuff is actually running on the RFSoC hardware. And now we will, as I said, have installed this loopback cable. And what I will show you now is that we will do this OFDM modulation scheme where we can play around with the subcarrier modulation. And so what I have to do here is I have to define the sample frequency of the DAC and ADC converters, which in our case is 4 gigasample. And then I can freely choose the center frequency of my radio transmission. So in that case, I set the radio transmission to be around 1.2 gigahertz. So let me quickly run this code. So then I will here configure the hardware to do so. And then I here have the, again, the block from my demonstration where I can change the subcarrier modulation scheme. So let me run this. And here I have a drop-down menu with the different modulation schemes, which I can later change. So, but first focus on the binary phase shift subcarrier modulation. And so let me then briefly run the demonstration. So I hope it works, but now we see here, this is a live update of the hardware. So the hardware is now running the OFDM transceiver, and it's modulating this random stream of bits on to the subcarriers using a binary phase shift keying. And you see this constellation plot, which is this IQ plot, and then this blobs here, so they are centered around and -1, correspond to signals having a phase of 0 and 180 degrees. And let's go one step further and change the modulation scheme in real time to the quadrature phase shift keying. So now you see the hardware changed. And here we have a quadrature phase shift keying being applied to all the subcarriers, where then actually two bits can be encoded. And to even go further, we can choose a different subcarrier modulation scheme. For example, this quadrature amplitude modulation scheme. So now let me quickly change that. And now you see this so-called constellation plot, and you see 16 different centers of where all the demodulated signals are spread around, and this allows you even to transmit more data with a larger throughput. And yeah, with this demonstration, we can really play around with the possibilities of using the RFSoC as a software-defined radio, and even go further. And for example, here to 128. And all of this is running in real time on the hardware. And I think with this demonstration now being working, I want to close the presentation from my side, and I would be happy to take and answer any questions which you have. Thank you.
Thank you very much, Johannes, for this insightful presentation. It's amazing what you did, and also very bold to present a live demo during a live webinar. Thank you very much. That demonstrates the level of expertise that you have. And yes, we gathered some questions that we have on the comments, but also from the form that we have for the registration form. And we realized that we not only have questions regarding the hardware, but also about the firmware. And for that, we decided to invite one of our experts that most of you already know, our lead FPGA SoC firmware engineer, Dr. Harry Coming, which we will invite to the studio so we can answer all these questions that we have gathered together. So, Dr. Harry Coming, welcome to the studio again. Yeah, it's a pleasure to have you here.
Thanks, Monica. It's my pleasure.
Thank you so much. So, if I may, I have this question. There is a question that it was actually thumbs up 6 times already, and it's talking about, would be great if you could touch on the synchronization qubits related to these RFSoC ADC and DAC channels.
So yeah, maybe I can say the first few things that sort of pop into my mind for that. So caveats, I sort of think of the limitations of the device. So the first thing that pops into my mind for that is the PLLs themselves in the DAC and ADC tiles are rather crude. So most of us are probably more familiar with using sort of MMCMs and PLLs within the FPGA fabric, which are very flexible and allow us to select basically any frequency we want, whereas the PLLs within the DAC and ADC tiles are somewhat limited. So for example, if you have a reference clock of 500 megahertz, then you cannot get the maximum DAC rate of 9.85 gigasamples per second out of the DAC, basically because that's not a multiple of 500 megahertz. And so the PLLs themselves have some limitations, and so I would maybe interpret that as a caveat. The second thing that came into my mind was multi-tile synchronization. So if you really want to synchronize the timing between the different tiles, then there are limitations on how you can configure things or how you must configure things. The one that pops into my mind is that you must power up and enable ADC tile 0 in order to enable multi-tile synchronization within the device. And I think there are some other caveats as well that are documented. So specifically for multi-tile synchronization, there are limitations to how you need to configure your RFSoC. The last thing that came into my mind was just clock forwarding in general. So you can forward either the reference clock or the sample clock between the different RF, DAC, and ADC tiles in the device. There are some limitations about what you can do there. And the main one that comes into my mind is that you can't jump over a tile. So you can forward a reference clock or a sample clock to an adjacent tile, but you can't jump over another tile that has some independent clock in it. You have to clock consecutively. You have to forward through consecutive tiles. So I'm not sure if they're quite caveats, but they're sort of limitations to how you need to configure the device in order to synchronize it. I hope that partly answers the question. I don't know if Johannes has anything more to add.
No, I think there are like a lot of caveats and things you also have to do right with the clocking of the RFSoC and also the sysref signals. But like I think in order to touch and explain all these details, that I think is a little bit beyond this webinar. But we can for sure come back to you if you have like some special questions and help you with the application.
Good. Thank you so much. And we have a second question. It says, are you directly synthesizing the sampling clock or a sample reference, which is then scaled to by the RFSoC PLLs? Do you observe any performance difference between those two methods?
That's a good question. So in the example which I have presented, we have generated the sample clock using the PLLs which are inside the RFSoC. So our sample, so our oscillator which is mounted on the RF front end has 500 megahertz, and then we use in each tile of the RFSoC there's a PLL which can generate the sample clock for each tile, so for each ADC and DAC. And then the question about the performance difference. So I think for this application we have not observed a difference, but I think there might be applications where it's very important. For example, if you look at the phase noise of the signals which you generate, then it's you are way better off if you directly provide a sample clock to the DAC converters. So you're not using the internal PLLs, but then your sample clock has to really be low in phase noise, and this will then also translate into an output signal that is low in phase noise, up to some limitations of the RFSoC. I hope that answered the question.
Thank you. And there's another question. How much is the isolation between the RX to RX channels, also TX2 to TX2, and the TX2 to TX, also this question?
Yeah, I think that's also a good question about the isolation between the channels. So ultimately, the limit you can achieve is what the RFSoC provides you with. So you have a certain isolation between the DACs and ADCs on the RFSoC, and in the frequency range, I think, what is it, above 4 gigahertz or above 2 gigahertz, at least you're limited to 60 or 70 dB isolation between worst. So that's the worst case isolation you will see. And so what we have done, we have also done measurements with our SOM and our RFSoC front end, and we have seen that we come close to that limit. So yeah, we are close to that values where we have about 60 dB isolation at 6 gigahertz.
Good. The next question is, in the introductory DAC example mentioning the 2 gigahertz signal and the 5 gigahertz sampling frequency, the original signal is inverted in the second Nyquist zone. Is this a problem in the application of heterogeneous sender and transmitters?
So it's true that it's inverted, but I have to think about this fact, and I'll come back to you.
Okay, perfect. Then the next question is, could you compare the use of such fast data converted with direct conversion versus the traditional approach with slower data converted and subsequent up-down conversion using analog mixers?
I think I made this comparison in the presentation where we have this direct synthesis. And so, yeah, so the advantage is just that the hardware is not as complex, and the signals which you generate with a direct RF generation approach, they have a huge bandwidth because the sample rate is high, and also the phase noise, if you do it correctly, is can be very low because you can generate a sample clock which is fixed in frequency, and this you can do not by maybe using a PLL, but using an analog multiplier chain, frequency multiplier chain, and then you will have a very clean sample clock signal that you can feed into the DAC converter, and this then allows you to be very good in phase noise compared to the other approach, and also you will suffer less from spurious frequency components if you do it correctly.
And also from the registration form, we have this as a comment and as a question about VNX plus form factor.
Okay. Yeah, so the VNX plus form factor. So the question is if the module can actually be accommodated in such a form factor. So the module which I've shown you in the presentation actually is a little bit too large to fit into the VNX plus form factor, but we are currently working on a smaller version of that module with a different RFSoC mounted that would fit in such form factor. Yeah.
And also from the registration form as well, we have this as a topic, beamforming IQ decode.
Yeah, so yeah, good question. Beamforming, yes, absolutely. The hardware is totally designed with beamforming in mind. The RFSoC device is absolutely designed with beamforming and other array signal processing applications in mind. We think of multi-tile synchronization. That's exactly what you need to do coherent array signal processing. Unfortunately, right now, we don't have a demonstration to show you with beamforming or array signal processing, which is a shame because actually my background is in radar and array signal processing. So hopefully that's something we'll be able to show you sometime in the near future.
Perfect.
Oh, and the other topic was IQ
decode.
Yeah, so I take that to mean IQ demodulation and modulation. And yeah, so that's something that the RFSoC device provides out of the box. So in the hardened silicon itself, in the DACs, it has complex to real conversion built in, and in the ADCs, it has the other way around. And so I expect for most people's use cases, they will just use that because it's free, it doesn't cost any programmable logic. If you have some very special requirement, like maybe you want to have some extremely sharp filter cutoff or something in that, then you could, of course, do that in the programmable logic if you have a special requirement. But I expect for most people, you'll just use the out-of-the-box product in the RFSoC.
Perfect. I have another question here. How many different RX or TX carriers are possible? Is it possible to have 8 different IQ rates or just 4?
So the question is about the RF channels, and Okay, so if I understand it correctly, so is it possible to have 8? So does it relate? So I'm not quite sure about that question. I will have a look and then come back to you later.
I could probably add one small thing to
Yeah.
that, which is that if you're really talking about signal carriers, you could, of course, modulate virtually any number of signals into a single RF channel and process them independently in the programmable logic. So it depends really if you're specifically asking about kind of independent RF channels, sort of going through different antennas, or if you're really just talking about different carriers, then you can modulate as many as you want, more or less, in the programmable logic. So some options there.
Okay, next question. How much is the effect of clock jitter on signal to noise? Does it not cause any problems at high frequencies?
I think in order to answer that, up to some limit, it should not matter. Or, only if it's very bad, then the jitter, which I think then would also translate to some high frequency noise. But typically, the oscillators which you use should be well below that limit.
Good. And is it possible to use an external reference clock, for example, 10 megahertz?
Okay, so I think I can answer that. So for the setup which we currently have, this would not be possible since the oscillator which we have running there is it's free running, but we are having a second RF front end now being designed where you could in principle also realize this case where an external reference clock can be fed into the module, and from that you can derive all the frequencies which then are sent to the RFSoC data converters and also the sysref and the clocking of the whole chip. Yes.
Good. Next question. Can you implement the CCS cosine raised to QPSK? Sorry.
In principle, we could do that by changing the firmware. Yes, that's possible, but we have not done that.
Okay, and the next question.
I think that's asking maybe about a root raised cosine filter. I'm not sure, but yeah, absolutely. Yeah. I mean, we can change the firmware however we like. That kind of filtering, yeah, absolutely. Why not? Yeah.
That's the advantage of software-defined radio, that you can just reconfigure the hardware.
Great. The next question, was the firmware for the ODFM application a Vivado project or a bitstream file or a RTL source code?
It is a Vivado project you can build, and that's the answer. And you can look at the different blocks, but you can't really go into each block and go to the very smallest detail level and look at the off-dim transceiver. But it's a Vivado project you can build from the GitHub repository.
Okay, it says this question. Do I understand correctly that whichever external sample clock reference is provided is used for both ADCs and DACs? So the phase relation is always fixed down to some phase jitter, but cannot drift apart?
So I think this question is related to phase drift between two channels. And I think, that depends on the clocking as described in the question, that you can also clock the data converters with individual sample clock or individual references. So there is some freedom about, for example, you could clock ADC 1 and 2, 3, 4 with one sample clock and the DACs with a different one. And then for sure you would have the problem that it could occur, or it will occur, that the phases will drift apart depending on the drift of your oscillators and the frequencies. But in general, the larger the frequency is, you would clock those, the smaller these phase drifts would be, or you would just clock them all from the same reference clock, and then you would not have that problem in so much detail. So great, yeah.
Good. And this question, do you have same board space qualified? I'm not sure.
Okay, I don't understand the question.
Okay, maybe we can elaborate later. If you, Francesco, if you can send us your question through the webinars@enclostra.com, and we can go back to you immediately.
I think it's asking if the hardware is qualified for use in space.
Ah.
I don't know the answer to that.
We are looking into that, yeah. But
okay.
We can for sure make it.
Okay, perfect. Then can you can run a modulated with DSPK transmitter and a receiver with QPSK modulation?
I think the answer is the same as this was for the other question, that in principle you can build whatever radio you want with the digital signal processing on the RFSoC.
Yeah, the modulation schemes are what you do in programmable logic. So you can choose any modulation scheme in the world, and you can transmit one. You can design a demodulator for another. It's completely configurable.
Okay. And we're almost running out of time, but I have another question. Could you explain about how change between different modulations? Are you using dynamic partial reconfiguration? I think there's three different questions. Could partially reconfiguration modules be relocated anywhere on the FPGA in real time?
I doubt that partial reconfiguration is how it's done, partly because the size of these demodulators would be so small. This is quite a big device. And I just think those demodulators are really very simple. You know, this is quite a simple example. Later in the year, we'll have some examples with some much more wideband processing, you know, looking at spectrum monitoring across gigahertz of bandwidth. This was a relatively narrow band example, and you would just instantiate them in parallel and switch between them to keep it simple.
What is the minimum time delay between RX and TX if we just retransmit received signal to TX using FPGA without any additional processing?
Great question.
Yes, so I think there we have to really go and have a look at that. So for sure, the data converters themselves, they have some delay, which also is not so insignificant. But I think in order to answer this question properly, we have to go and have a look.
Yeah,
okay.
It sounds like a jamming application. This is always a very important question. Yeah, we don't have the answer yet.
Good. And what is the maximum power, input, output, and dynamic range of the embedded converters?
So the input power, so the converters have a differential output, and if you do the conversion from differential to single-ended, then you have several dBms for the output of the DAC. So like 5 dBm, I think, is the number which you achieve with full scale. And then for the input, you can actually configure the ADC to also have some adjustable attenuation in front of it, and then even deal with a slightly larger powers than a few dBm, so above 10, if you configure the ADC correctly.
Okay, we are running out of time, and if we have some other questions, please, everybody, if you want to send us your questions, we will gather this information, and we will go back to you please write to us to webinars@enclostra.com, and we will get back to you with all the questions that you may have. And just for conclude, I want to invite you to consider the Enclostra RFSoC SOM for your projects. This compact module, as our experts just explained, it was developed around the AMD Xilinx RFSoC, which allows you to considerably reduce your time and your design effort for SDR, for radar, and for other applications. Also, please take advantage of this engineers' know-how, as you can see, our experts, to cut the short development time for your products with our design services as well. So we gather all this information, everybody. If you have any more questions, feedback of the topics that you want us to take in our next webinar, please write to us. And if you want to receive the presentation or the recording, please also write to us, and we will send it back to you. But until next time, this is everything. Thank you so much, Johannes. Thank you, Harry, and see you next time. Thank you so much.
Bye.
Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.